All right, this is part 2 of our projectile motion conversation. In part 1, we looked at an object just being fired out of a window. I called it case 1. It's a horizontal launching situation, and we broke it up into a vertical and horizontal thinking. Well, we're going to continue with that thought, only this time we're going to launch things at angles. Okay, and the angle part is important because by launching an object at an angle, you create not only a horizontal piece, but also a vertical piece. And that's going to change the way we solve problems a little bit. How we set up those angles and how we break them down, that's going to be our components method we've discussed previously with displacements and other vector velocities. So all of the same skills, we just have to sort of integrate them into projectile motion. So on this one, picture here, you can see there is a green initial vector, and it has been broken down into its two components, Vix and Viy. Okay, so that's going to be how we're approaching. I'll do two cases. One case will be this one, where we have angular launching from the ground, or our zero reference. Okay, and there's going to be some interesting things that we pull apart from this. And then we'll do one that's going to be on an angle and elevated, and that changes a few other pieces. So we have a soccer player running on a level playing field. They kick a soccer ball with a velocity of 9.4 meters per second at an angle of 40 degrees above the horizontal. Determine the soccer ball's time of flight, range, and maximum height. We may not do those in that order, but we'll get all three of them in here. So we have a picture. I've identified the maximum height is somewhere at the top of this parabola shape pathway. And then we have the components down here, the soccer ball with Vi, that's the initial velocity. So this is 9.4 meters per second. And now we're going to break it down and find Vix, or the initial horizontal velocity and the initial vertical velocity. So if we use our cosine, I probably won't be able to write all that down, cos 40 times 9.4. There's a dot there. This should become 7.2 meters per second is our Vx to start the problem. If we do sine 40 and we multiply that by 9.4, we get 6 meters per second for our Vy. So those are our components. Okay, so we're going to break the 9.4 down into a vertical 6 and a horizontal 7.2. Okay. So now we're also going to chop this problem up into not just vertical and horizontal, but we're also going to turn it into parts of a problem. So our first part of the problem is going to be going from ground to the max height. And we choose the max height for a reason, because at the max height, that's this location right here, something happens to the vertical velocity. And if you think back to one-dimensional motion where we were throwing objects in the air, okay, at the maximum height that the object reached, it would stop for an instant. So at this maximum height right here, we know that the vertical velocity is 0. Not the horizontal velocity, just the vertical velocity. So when we have the part 1 going ground to max, here is what we can list. We have the initial velocity is 6 meters per second. Okay, and this is all vertical information. If you want to put in the subscript y, you're allowed to. I'm going to avoid it just because it gets a bit messy. We have a final velocity of 0 meters per second, and I like to add the statement that's at the top. We have an acceleration of negative 9.8 meters per second squared. And if we want to try and figure out the time of flight, the range, and the maximum height, we need to find both d and t for this particular question. So if we want to go after t, we can use Vf equals Vi plus a t. That would be our kinematic equation. So Vf is 0. Vi is positive 6 because it's pointing upward. Our acceleration is negative 9.8. And t we do not know. If we rearrange and solve for t. 6 divided by 9.8, we would have 0.61 seconds. Now, we have to remember what that means. That is the time to get to this location, the max height. So this is 0.61 seconds worth of time. Now, we can take advantage of our level playing field. We talked about this in the one-dimensional motion. If an object starts at 0 reference point, is thrown up into the air, and then comes back down to that same 0 reference point, then what we found from symmetry was that we could double the time. So the time to fall back down to the ground would be 0.61 seconds as well. In our next example, we won't have symmetry, and so we'll have to approach the problem in a slightly different manner. Okay? So there's our time. Our flight time would be 2 times 0.61, so our flight time is 1.22 seconds. If we wanted to set that up though and just verify that symmetry, if we went from the max height to the ground, we would say our initial velocity is 0 meters per second. Our acceleration is negative 9.8 meters per second. And we would need some more information because I don't know what VF is without assuming symmetry. And I don't know what D is. So I would have to do some more work. Okay, so now if I jump back up to ground to max height, our next piece we could calculate within there would be to find the max height. So let's just cut this off. It's getting a little messy, my apologies. So to find the max height, we know we have an initial velocity of 6, a final of 0, an acceleration. So we could use, I believe it's number 4. And then we could substitute in our values. And this will allow me to solve for the max height. If you want to use an h instead of a d, you're welcome to do that. So 0 equals 36 minus 19.6d. We'll rearrange and do our division. Oops, so 36 divided by 19.6, and we get 1.84 meters is our max height. Okay, so if we scrolled back up to the top here, this height right here is 1.84, did I say that, meters, for max height. Okay, now if we didn't want to believe symmetry, we could bring that over here and say this is 1.84 meters, but it would be negative because we're going from max height down to ground. And then we could reuse that expression, and so this time we would solve for VF. Okay, and you could probably start to see, because we're using the same numbers all the time, this is why we get or generate the same values that we originally started with. Okay, so plus 2 negative 9.8 times 1.84, which is also a negative. And then if we multiply all that out, not a great big surprise here. And I'm going to put the negative on there because I know it's down. Okay, and what we see is the information from max height to ground. We show that the velocity is the same. We could use another expression and find that the time is the same. So we could take advantage of some of those symmetry operations with this type of question. The key, though, is that we have to break this down into purely vertical thinking. Okay, so we now have the total flight time, we have the maximum height, and now we just have to go after range. And range will be a combination of our Vx term and our flight time. Okay, so our range, let's go a little further here. Because there is no acceleration, we can use v equals d over t, where velocity was, I believe, better double check, 7.2 meters per second, and time was 1.22 seconds. So if we insert those into our equation and solve for d, which in this case is our range, we get a d value of 7.2 times, oops, back up on the calculator, times 1.22, and we should get 8.8 meters. And that would be downfield, to the right, some direction that works. Okay? So again, very broken up, fragmented thinking. You have an up-down section, and you have a left-right section. That's case 2. Okay, now case 3 doesn't have symmetry, so we're going to have to do a little bit more work here. And again, we're going to break this in a vertical, okay, and we're going to bring it in a horizontal, and then we're even going to break the problem within the vertical from ground to max height and max height to ground. Now there is no symmetry in this question, so we can't do any shortcuts, so we're going to have to do this with a little bit more writing. So let's start with finding our components. That would be the first piece. Initial velocity, that's really important to read that in the opening part of this question. That is this value here. That is the resultant. That is the 25 meters per second. Okay, at 50 degrees above the horizontal. So there's 50 degrees in there. So if we do cosine 50 times 25, we get a Vx of 16.1 meters per second. If we do sine 50 times 25, we get a Vy of 19.2 meters per second. So this is Vy, this is Vx. Okay, so those are the components. That's the first thing you want to do. So now we're going to work this problem. We are going to go from ground, which is this location here, to this maximum height right here, and that's going to be the first half of the problem. So I'm going to write a little bit smaller. So we have a Vi of 19.2. We have a Vf of 0 at the top, because we're looking for the max height. We have an A of negative 9.8 meters per second squared, and we would like to find T and D in this little time. Let's see if I can move this down. Oh, good, I can. Get you out of here. There we are. All right, so if we want to find our time, we can go Vf equals Vi plus At. 0 equals 19.2 minus 9.8 for T. And I'm going to just save a line. By the time we solve that, it's 1.95 seconds equals T. Okay, so we now have our time value. Okay, and then we will do find our D. So we should be able to do Vf squared Vi squared plus 2AD. So 0, 19.2 squared plus 2 negative 9.8D. I'm going to do a little bit of this on the calculator only because I'm running out of space. Okay, so 19.2 squared divided by 2 times 19.8, and I should get 9.3 is my D. Okay, meters, and that is up because it's positive. Okay, so I know that this little height right here is 9.3 meters. Okay, so I found the time and the max height measured from the start of the problem. Now the second part of the problem is going from the max height back down to the ground. So let's list what we know. At the max height, the V initial is 0. Acceleration is negative 9.8 meters per second squared. I know D now. Okay, I know D is the distance I have to fall back down to the ground. So that is this 9.3 plus the original 30 of the cliff. So I have negative 39.3 meters is the displacement I will have by the time I fall all the way back to the ground. I don't know VF, and I don't know time. Okay, so let's just have a look. Range, final velocity. Okay, right before it hits the ground. So we're going to need both of those pieces. Let's move components over there. So if we want to find the time, VF equals VI plus AT. You'll notice there's some repetition in the solving technique. So VF, oh, but see, now I've hit a problem. If I go to solve this, I have VI, I have A, but I don't have the time value. Oh, so now I need to have a different approach. Okay, so that one is out the door. So let's try again. What about equation number 3? So if we went D equals VIT plus 1/2 AT squared. Let's go through. We know this. This is going to 0 and take the t with it. We know this. We know this. We want the t. All right, this could work. So now let's go back. Negative 39.3 is d. Vi is 0, so it's going to take that t with it. Acceleration's negative 9.8, and t squared we don't know. Okay, so I'm going to just do one more line. Okay, so we're going to take that 39.3 divided by 4.9, hit equals, and then take the square root of that value, and we get 2.83 seconds equals time. Okay, so we now have our time. Oops, seconds. Okay, so if we were to look at this picture, we could see the first component. Let's drop this line down right here. And we'll draw this across here. This took 1.95 seconds to go from the start of the problem to the max height. It then took 2.83 seconds to go from the max height back down to the ground. So the total time would be those two values added together. So 4.78 seconds. And you can see, because we don't have symmetry, these values are different. That's really, really important. Okay, so now we also need VF before we can answer the last question here. We have 2 more questions to do. So VF, we want to know, we know the time now, so we can go back and use this guy if we like. So VF is going to be 0 minus 9.8 times 2.83. Okay, and 9.8 times 2.83 is 27.7 meters per second, and it is negative because it is down. Now again, because of symmetry, or a lack of symmetry, this negative 27.7 is larger than the initial 19.2 meters per second we had in the vertical direction. So that would make sense. If we had stopped at the same height we started, we would have had a 19.2 here. But because we're allowed to fall further, we have a 27.7, I think I said, in 27.7 in the vertical direction. Okay, so let's go back and look at what we found. We need to know the time of flight. We have that, 4.78 seconds. We're going to use that to find the range and the final velocity. That's going to be a challenging piece. Okay, so let's do the final velocity while we're on this page, just because the information's here. Right before this object hits the ground, it has 2 vectors. It has a 27.7 meters per second vector going down, and it also has the horizontal vector up here of 16.1. That's this guy right here. Now we can use those 2 vectors together to make a resultant by relocating some of them, and then we can do a quick Pythagorean theorem. Okay, so our resultant here is 27.7 squared plus 16.1 squared. 27.7 squared plus 16.1 squared. Oops, don't make sure we got that. And then square root that. 32 meters per second. Now that's half of an answer. We don't have a direction, so we need to find our angle theta here. Tan theta is going to be 16.1 over 27.7. And then we take the arctan of that. We should get 30 degrees. 30.2 actually. Now again, that's kind of floating out in space. So we need to give a little bit more information on what the velocity is right before it hits the ground. So I would probably write it this way. I would use my sum of interior angles, and I would say this is 60 degrees. So I would say this is at 60 degrees to the horizontal. Okay, and that would be one way of describing that vector. Okay, as long as you have a good picture, that helps a lot. Then lastly, and I'm sorry this is going on a long time, but these are big questions, that's why I tried to split it up. Range. Okay, and range is our simple equation with no acceleration. Time, our total flight time, way back at the top, is 4.78 seconds. Our velocity in the x direction was 16.1 meters per second. And if we substitute those values in, we can find our range just by multiplying them together. So 16.1 times 4.78 is 77 meters. So that would be our range. Okay, so there's lots going on there. I fully expect you to have to pause that, rewind, scrub back and forth. But again, it's breaking the problem down into smaller parts. Go from vertical and horizontal, separate the thinking. Break it up from ground to max height to ground. Find all the missing pieces. And then the last part is the horizontal and the range, and that brings it all together. Okay, so not a lot. On page 81, there's 4 questions to try. Should be one from each case. Thanks for tuning in.